Everyone. Welcome to today's webinar, Multi-Layer Ceramic Capacitors, a Deep UV Success Story, hosted by Dr. Katherine P. Rice at CAMECA. We're going to give everyone about another 15 seconds to get in the room, and then our presentation will begin. Comfortably begin today's presentation, so I'm going to throw to Katherine. Dr. Rice.
Hi, everyone, and thanks so much for joining us today. My name is Katherine Rice. I'm the Applications and Market Development Manager here at CAMECA in Madison, Wisconsin, and we are very excited today to also be joined in a live Q&A with Dr. Severin Jakob, currently at the Institute of Thermomechanics at the Czech Academy of Sciences. We're really looking forward to your questions after the recorded webinar, so we'll see you in a few minutes then. Hi, my name is Katherine Rice. I'm the Application and Market Development Manager here at CAMECA in Madison, Wisconsin. In this webinar, I'll be talking about a relatively new application to the atom probe in multi-layer ceramic capacitors, or MLCC materials. These are really exciting because it's where deep UV has made a really big difference in the success rates. And these are also really important to everyday life. They're used in almost every cell phone, every computer, things like that. So these are really critical pieces of technology that we may not even recognize. After this short recorded presentation, we'll jump into the live Q&A, which I love hearing your questions. So let's get started. So what are MLCC materials? These are essentially small capacitors which are integrated within almost every microelectronics device. So think your TV, your cell phone, your laptop, anything like that. And we have a picture here of some of the MLCC materials which are put together inside an actual circuit. You can see here all these little kind of rectangular things are the multi-layer ceramic capacitors, and they're typically part of larger electronic circuit boards. And the purpose of them is to act as capacitors, so they manage power delivery, stabilize voltage, and store charge for these different applications. So you can imagine something like your cell phone. You have to manage power intake from the charging and power outflow from all these applications that you might use in your cell phone. And this market for MLCCs is actually quite large, about 23 billion. Most manufacturers are based in Asia. And just to give you an idea, that market size is pretty similar to the AI chatbot market. So you can think about, every time you call a customer service, you're faced with an AI chatbot. Every time you pick up an electronic device, you're handling these MLCC materials. So what do these actually look like? These tiny rectangles, if we kind of cross-section and cut one in half, what we'll see are interleaved layers of ceramic dielectrics and metal electrode materials. So here's an SEM image of one that was cross-sectioned or cut in half. These bright areas in this case are nickel electrodes, and these darker regions are a barium titanate based ceramic. And we'll talk a little bit more about why barium titanate is used in the coming slides. The higher the capacitor rating, typically there's more and more layers of these things, and they're rated by size. We can have different materials, but barium titanate and nickel are among the most common. You can have other electrode materials like copper. You can have other ceramics such as strontium zirconate, for example. And so let's take a look at why barium titanate is used specifically in these applications. The overall goal of MLCC materials is a maximum capacitance, or the ability to store charge, in a minimum footprint. Now we also have to consider how this might interact at typical operating temperatures that we face in modern electronics. And one of the materials that we see quite frequently in the lab here and when we've purchased off-the-shelf devices is barium titanate, BaTiO3. And this figure will show a little bit about why that's the case. It's a material that has a high intrinsic permittivity. Now, if we think about our capacitance, that's going to be a function of how many layers we have, the permittivity, the area, and the layer thickness. Here in this figure, we have permittivity over Curie temperature, And the Curie temperature is where we're going to have a ferroelectric regime and a paraelectric regime. The MLCCs are typically operating within this 55 to 155 Celsius operating temperature. And really what we want to do is have our Curie temperature match our typical operating temperatures or room temperature for a lot of electronics or a little bit higher. Now the way that we can influence this Curie temperature is by doping. And a lot of rare earths are involved, particularly in doping this to modify that Curie temperature to be in typical operating regimes. Now, as folks are studying MLCCs and the common problems, really what we're trying to do is investigate how the grain and core shell structures that are formed influence their properties, how temperature might affect them, and since there's a lot going on in these capacitors, how different phases and segregation might affect those as well. So as you can imagine, this is all happening in 3D, and atom probe is a really good technique to use when investigating this kind of nanoscale behavior. And we can take a look at a couple different aspects of MLCCs and things that we might be able to study with the atom probe. Let's keep in mind the overall goal of research on MLCCs, which is to have a highly insulating capacitor at minimum footprint that's reliable at different operating temperatures. Now, one way to achieve that is by doping, and that involves modifying the chemistry of our barium titanate matrix to change the properties. And one of the ways to do that is doping with rare earths, particularly dysprosium. This is a really interesting element because it has a 3+ valence state, so it can substitute at the A sites for barium 2+ or the B sites for titanium 4+ and act either as a donor or an acceptor. Now, donors are needed because we need to have stabilized electric properties and reduce oxygen vacancies. The acceptors can really contribute to improved insulation properties. Now, dysprosium is among rare earth elements with 3+ valence states, but as we can see here in the table, it's often used for barium titanate because it has a lower cost than other elements such as gadolinium or holmium. Another piece of this is the structure that forms on MLCC synthesis, which is a big contributing factor to the operation of the devices. What we're really after here is a core shell structure where we have a ferroelectric barium titanate core and a paraelectric doped shell. The idea here is within that ceramic layer, we have a number of these different core shell structures in 3D with the largest amount of insulating core volume that we can, but a uniform shell that can kind of limit oxygen vacancy diffusion between cores. And so, as you might imagine, with both doping questions and structure questions, the atom probe is a really good technique for MLCC research. Okay, so how do we actually get data from these great devices? And I have to say this is one of the most cost-effective applications development projects that we've done in recent years because I think we ordered 3 of these MLCC devices off the shelf for less than $1. Now, these are very tiny devices. The ones that we received were from manufacturer Murata, I believe in Japan. And these are rated by size, so you can order different size devices, but you don't really know what kind of chemistry you're going to get because this could be a strontium zirconate, this could be copper-based electrodes. But here what we've done is actually taken one of these small devices, just about a millimeter cubed, and we want to probe the interior of the device. We can look at the interface between those electrodes, metal electrodes, and that ceramic capacitor. What we've done here is actually put this in a metallographic mounting press. Here we're just using a copper washer to both hold it and provide a guide for where the bottom surface is. And we can mechanically polish that down so that the interior of that MLCC is actually visible to us on the surface of the SEM. Here we've also used a little bit of copper tape just to help things be more conductive, because if you've worked with metallographic mounts in the past, you may know that these are epoxy-based and not always super conductive in the SEM. So sample prep is obviously so important both for electron microscopy and atom probe, and we can approach sample preparation of MLCCs in a couple of different ways. And there's some unique considerations for these type of materials. As you can see from the surface, here we have in this top image A, those bright regions are our nickel-based electrodes, and those darker regions are the ceramic material. Here we've done a standard top-down lift-out process, in which case you will generally be getting several different layers of MLCC electrodes and ceramics. In this case, you may want to adjust your annular milling pattern to target one specific region. In this case, you can see in the mounted wedge in C that we have electrodes material on both sides, and we've centered our annular milling pattern such that we're actually sampling the barium titanate region in our mounted wedge, which is, the goal of this region of interest. One of the things that you can typically see sometimes with perovskites is a terracing as your annular milling. So that'll lead to kind of a wedding cake type shape as you push down in your annular mill. One of the things that you can do is mill with higher beam currents to mitigate that a little bit. Now, if you're studying MLCCs, one thing I would recommend is trying sample prep in different directions so that you can sample different aspects of this device. Now, a lot of times we know that interesting things are happening at interfaces. So in this case, we wanted to sample or have in our final tip the interface between our metal electrodes and our ceramic material. Now, to do this most effectively, we've chosen to prepare that sample in cross-section. And this is detailed in our technical note 04 if you're not familiar with the process. But just to give you a quick overview, what we do here is pull a wedge, and then we mount this to a transfer arm. This is in the fib stages that we offer for sale here at Kamika. And that will allow us to rotate this at 90 degrees, recut the wedge so that we have the interface between our electrode and our ceramic within each mounted wedge. Now, when we mill this with our annular mill process, we can adjust our final stopping point with our low kV milling so that we're end pointing the final tip shape so that it has that interface between our electrode and ceramic pretty close to the apex of that material. And that's going to give us a really high chance of success to collect that in an atom probe analysis. The other thing I want to point out in these are the presence of voided regions in the mounted wedge that you can see here in image D. A lot of times these don't extend all the way through your pulled wedge here, so you can just generally skip one mounted chunk if you need to avoid that. A lot of times having a voided region in your tip will lead to low success rates. Cross-section sample prep can be a highly effective way to analyze the interface between those metal and ceramic regions. Okay, so just to give you an overview of what you can expect from the atom probe data of MLCCs. In this off-the-shelf example, we were successful in getting a nickel electrode and a barium titanate ceramic. Again, if you're working with off-the-shelf MLCCs, you can get a variety of different perovskite types. Most of the time, the electrodes that you're going to see are, in fact, nickel. So these run very well in the LEAP 6000 XR and in VISO 6000. We'll talk a little bit about the reasons why that might be the case later on in the webinar. Now, if we look at the mass spectrum from these devices, we see that it's relatively complex, which makes atom probe fun. We have our major elements of barium and titanium oxide, plenty of oxide species as you might expect, but we also have a large amount of different types of dopants and minor species. So for example, we have clearly presence of dysprosium oxide confirmed by the isotopic signature, but we can also see things like tin, zirconium, yttrium, and manganese, all as dopants which are modifying those properties. So we can take a closer look at how those dopant elements might be distributed. So let's keep in mind our overall goals of this analysis is to look at the chemistry and look at the structure and particularly how these dopant atoms are distributed. Now the first thing that we can see here is pretty clear evidence of core regions, which is a relatively dopant-free regime, kind of circular or maybe even a little bit faceted in nature, surrounded by a shell of doped regions. Now we can look at that a little bit more closely in 3 dimensions. Here we have an isosurface of dysprosium, zirconium, and nickel, which is highlighting these regions where we can kind of define a core. Now that's going to allow us to look at the bulk composition within these cores and compare them to the shell regions. And what we find here is that our shell is pretty heavily enriched, a little bit less than 0.5% in dysprosium, whereas as we go to the core regime in our bulk composition, we're really not detecting any of those special dopant atoms such as zirconium and dysprosium. We can also look at the approximate size and uniformity of this shell, and we find that it's kind of a different phase. It's still BTO, but with the significant presence of both dysprosium and zirconium. This forms about a 20 nanometer thick shell, which is sufficient, if we look in the literature, to provide that barrier of conduction from core to core in our MLCC materials. So in this case, it's a good thing that we observe that, because that's telling us that our cores are relatively insulated as ferroelectric regimes from the paraelectric regime of the shells. The other thing that we see a ton of in off-the-shelf MLCC materials is grain boundaries. And I have to tell you, this research is so much fun because we have the presence of multiple phases, grain boundaries, and all kinds of stuff going on. So it's really a playground for material science. But if we look at these grain boundaries, one of the things that we can do is look at what is segregating to those grain boundaries. And we can do this in a couple of different ways, but one of the standard ways in Atom Probe is to look at the interfacial excess, and that's going to give us a normalized amount of segregation at the grain boundary. So the way that this is calculated is we're going to measure the species level, so whatever species we're interested in, at the grain boundary, and subtract that species level at the matrix. So this is the amount over and above what is in the matrix. And then we're going to divide that by the sampling area to have an area normalized measurement of segregation. Now, the cool thing is that one of our extensions in AP Suite can do this automatically. This is the Gibbs Interfacial Excess extension in AP Suite, and that's going to allow us to quickly and easily do this calculation for a number of different species that may be segregating. So we've done this here closer to the electrode here. I've kind of cropped that out of this particular image, but at the top of the screen, that's where that nickel electrode is since we prepared this sample in cross-section. And the second ROI here, region of interest, is closer down into the bulk of the material, and this is just above one of these shell regions, so we've kind of excluded that from the analysis. But one of the things that we can do is look at how different species might be segregating kind of at the top close to the electrode and lower down in the ceramic matrix. Now, once we do this interfacial excess calculation, we can compare that for different elements as we go to different regions. So here I've called this upper region closer to the electrode, and the lower region is closer to the matrix. Now, one thing that we find, which is maybe not that surprising, is that we have quite a bit more nickel closer to the electrode. Well, that's an interesting observation because, nickel's a metallic element. So if we see diffusion from our metallic electrode into our ceramic, which is supposed to be insulating, this can be pretty detrimental to the operation of the device because you now have metal migration into your ceramic insulator. Now we can repeat this analysis of interfacial excess for these other dopant atoms that we see, so dysprosium and zirconium. And we see that these are segregating more strongly closer into the matrix. Again, not that surprising, but if we look at these different directions, we see that the nickel may be diffusing down from the top from our electrode region, and our rare earths might be diffusing up along the grain boundary. So that's going to give us a little bit of an insight into how things might be moving or migrating inside these core shell structures. Now, one of the exciting things is that new technology is really making a difference for the analysis of MLCC materials, and I'd like to briefly touch on 3 different aspects of this. One is photoionization, or perhaps different mechanisms for field evaporation in deep UV. The second is an option called scripted acquisition, which can help improve yield at interfaces. And finally, voltage plus laser on the LEAP 6000 XR, which can help improve data quality in our mass spectrum. So let's take a look at each of these three newer technologies. Now, the best evidence that we have for increased success rates with perovskites is a new evaporation model proposed by Dr. Severin Jakob at Chalmers University of Technology. And we are in for a very special treat because he will be joining us for the live Q&A. Now, what the authors did in this case was compare UV and deep UV instrumentations with a couple of different materials. For metals like nickel chromium alloys, the evaporation should proceed in a predictable way. So as you increase laser pulse energy, your detection rate should also increase according to an Arrhenius evaporation model. And that is the case in deep UV and UV for metals, but not the case for certain kinds of oxides. Now, the authors here compared thermally grown chromia, so chromium oxide, and a perovskite material of strontium titanate. And what they really found is that increasing your laser pulse energy caused your field evaporation or detection rate to proceed in a way that wasn't quite the same as it did for metals. So there must be something else going on rather than just a shot of thermal energy which would directly relate into field evaporation. So the authors propose that this might be related to photoionization because these materials have band gaps which are closer matched to deep UV compared to UV. And the new proposed mechanism suggests that holes might be generated and gather at the apex of your needle. These holes would be created by that photoionization mechanism, and that would lower the activation energy for atoms to evaporate. And this process is really rate limited by how fast holes could be generated from the deep UV laser pulse. Now, I am not an expert on this, and Dr. Jakob will be here for the live Q&A, so please save your questions for him as a truly excellent scientist working on the fundamentals of field evaporation. We can also use some newer technology called scripted acquisition to help improve our success rates and data quality. Now, in the case of our off-the-shelf MLCCs, one of the things that we're interested in is the interface between those nickel electrodes and our barium titanate matrix. Because again, interesting things happen at interfaces. Now, as you might imagine, a metal and a ceramic might have different field evaporation behavior and different preferred conditions in the atom probe acquisition. So one of the things that we can do is choose different acquisition conditions to be applied automatically at different stages of our acquisition. So for example, as we're evaporating through our nickel electrode, we can choose a set of acquisition conditions to be applied. And when we reach a trigger criteria, that could be something like a particular voltage. It could be the concentration of a certain element in our mass spectrum. So for example, when we see 2% barium in our mass spectrum, that can change our acquisition conditions to a second set of user-specified acquisition conditions. And this is going to help make sure that the conditions that we're using are appropriate for each different material type and increase the success rate of obtaining that interface. This can also help improve our data quality. So in this case, I'm showing the voltage evolution, so the voltage curve as we are acquiring data as we go from our barium titanate ceramic to our nickel electrode. So in this case, we've flipped around our sample prep so that our ceramic is on top. Now in this case, we've chosen a set of acquisition conditions for barium, which is not the same as our nickel electrode. But as we change those, we can see that our voltage curve was quite smooth throughout that transition zone as we go from one material to another because we are dynamically changing those conditions to be most appropriate for those materials. Now, what we don't want to see as we go through interfaces are really sharp transitions. That can affect our reconstruction, and that can affect our confidence in being sure that we've actually collected and not broken through our interface. So by using scripted acquisition, we can choose appropriate acquisition conditions reduce the stress on the specimen and lead to higher success rates through interfaces. So finally, the last thing that can really help us out here with new technology in the analysis of MLCC materials is simultaneous voltage pulsing. This is technology available in the LEAP 6000 XR, and what that means is essentially pulsing with a voltage and laser pulse simultaneously. So these are synced together to hit the sample with both a laser and a voltage pulse at the same time. Now, the primary goal of this is to reduce the background noise. As we already talked about, this is already quite low in the MLCC ceramic materials with deep UV, but there's always improvements that can be made. And the secondary advantage of simultaneous voltage pulsing is to change and modify your mass spectral peak shapes. So the way this works is we can have a voltage pulse which is variable and can be moved slightly relative to the fixed laser pulse. And one of the things that this allows the user to do is slightly offset them. So you could offset your voltage and laser pulse so that one is slightly earlier or later in time, and change your pulse shape that's actually interacting with the specimen. Now, you may want to do this because each material has different ways of interacting with the laser pulse and the voltage pulse. The thermal and electrical conductivities can be different per material type. And as we've seen here with Dr. Jakob's work, maybe there's additional field evaporation behavior going on with the photoionization mechanisms. So that being said, one of the things that we can do is offset these slightly to change our peak shape, which has the major advantage of reducing peak tails. Now, as we saw earlier in this webinar, the mass spectrum of these materials is really complicated. So you can have minor elements that are occurring in the tails of another peak, making it really hard to determine how to range that data. So one thing I'd like to show you here is we can compare laser pulsing here in red. This is the mass spectral peaks by using standard laser acquisition at 25 picojoules for this MLCC material. And if we choose a voltage plus laser or simultaneous voltage pulse with a 5 nanosecond offset of the voltage pulse relative to the laser pulse, one of the things that we can see is we can dramatically reduce the tail of our barium peak between 68 and 69 Daltons. And that gives us a major advantage of being able to make our peak sharper and look for elements that might be occurring in the tail of our barium or another peak. The other advantage that simultaneous voltage pulsing has for MLCCs is to improve the mass resolving power. So we can compare that to our laser only pulsing mode here, that's 25 picojoules. We've compared the full width half max, 10th max, and 100th max of different acquisition conditions for voltage plus laser. So by comparison to full width half max in laser only mode, we're quite a bit higher, about 10% higher in mass resolving power when we choose a voltage plus laser with a 6 nanosecond delay. But one thing that we can see here is as we continue to analyze our mass resolving power closer to the bottom of our mass spectrum, so these are the full width 100th and 1000th max, we see much larger improvements in mass resolving power. So our peaks are getting really sharp at the noise floor of the data. And if we can reduce that background of our peak and improve our mass resolving power, that's going to give us better data quality and help us to find those low concentration elements. So voltage plus laser is something worth considering if you're analyzing MLCC materials. Now finally, to sum up and offer a few thanks, MLCCs are a critical part of most modern microelectronics, and these are generally pretty overlooked. You don't think about how your capacitors in your cell phone are affecting your day-to-day life, but they need to be reliable at different operating temperatures and different voltages for a very long time. Now, a key piece of this is investigating the structure-property relationships, and Atom Probe is a really great tool to do so because we can look at things like doping, concentrations, and distributions in our core shell structures. We can look at how things are segregating and diffusing in the devices, which are really important to relate to how these materials are synthesized. Now, deep UV atom probes are making a very positive difference in the analysis of these materials, leading to much larger data sets. We can speculate to why that's the case, perhaps a new photoionization mechanism, and I'm so glad Dr. Severin is here to talk about that with us. And we can also use some new technologies such as scripted acquisition and deep UV to both improve success rates at interfaces and improve data quality. Now, I'd like to offer thanks to my colleagues here at CAMICA, but also particular thanks to Dr. Yiming Chen at Eurofins Nanolab. We've been working with Dr. Chen here for more than 10 years, and he did most of the work in the sample prep and acquisition of these materials. Really great work. And I'd like to also recognize Dr. Severin Jakob, who's here for the live Q&A. He graciously agreed to be here to discuss his new proposed mechanism for photoionization, which I think is super exciting. So at this point, the pre-recorded portion will finish up and we'll jump into the live Q&A. I'm so excited to see you there, and thank you so much for watching. Okay, I think we're ready to get started on the live Q&A. We have quite a few questions already rolling in, so thank you, Severin, for being here, and let's get started. All right, first question, I think it's for me. On the segregation slide, could the nickel diffusion be caused by fib preparation? Now, this is a good question because when we're doing that annular mill process, we are pushing ions around. Now, the fib-induced damage typically, it's dependent on the energy that you're using for that annular mill. It typically doesn't extend too far, even as knock-on damage. So we can use the gallium protrusion into the material as a guide for how much damage we expect. And we can also consider, let's say, another exclusion zone where we don't see gallium diffusion, but we do see what's called knock-on damage. Now, that probably extends something like 30 to 50 nanometers for typical high energy milling, so at 30 kV. And the segregation that we're seeing from nickel is, 80 to 100 nanometers away from that apex. So it's pretty far away from where I would expect gallium to have an influence. So I would say it's possible, but in this case, it's a bit far to expect gallium milling effects. Okay. Next question, did you see any strange behavior in the mass spectrum due to the interaction of the laser with the material? Was there any influence on the hydrogen peaks? Now, I'm not sure if this attendee is referring to voltage plus laser or just the fact that we're evaporating perovskites with laser. What you can expect is a reduction in background in general. This isn't typically going to affect a specific peak, so you're almost always going to see a hydrogen signal in your mass spectrum if you're using laser mode. So if you're doing serious hydrogen analysis, you'd want to be doing deuterium doping and running in voltage pulsing mode without the influence of laser. So I'd say, although V plus L can help reduce background in general, it's not necessarily going to have a preferential effect on hydrogen. Now, as far as evaporating MLCC materials with laser, this is, leading to a high presence of complex ions. We don't see a lot of hydrides in this material. I would say typical laser energies that we used are something like 25 picojoules. So, okay. Could the offset-induced peak shape improvements be masking delayed evaporation effects rather than fundamentally improving mass resolution? I think that's a good question, and I think that that's certainly very possible. You're changing your pulse shape and you're changing your peak shape. So, how this peak shape is influenced is going to be dependent on how that's dissipating the pulse, both voltage pulse and laser pulse. And you might just be shifting some of your delayed evaporation earlier in time of flight. Okay. So Severin, this one's for you. Thank you for the great presentation. Do you think that photoionization is limited to materials that have a band gap? Or could it also contribute to field evaporation of conductive materials that have a similar work function as the photon energy? What do you think?
Thanks for the very good question. I think that the band gap is a criterion to see this form of evaporation. And I think that the work function is then the next criterion to see effective hole generation, to really see the difference to a thermal pulse. And even going back to the basic of the what we've seen is that we need hole accumulation at the apex. So we need to get many holes in there to reduce the activation energy for desorption. And if we have like a metal, then those holes would recombine with the electrons that are in the material. So I don't think that we would see this form of evaporation with metals or with like very low band gap materials or
Thanks.
conductive or highly conductive materials.
And that kind of makes me think, just to jump in before our next question, this idea of in situ coating. So applying a coating in the fib using redeposited materials. I'm envisioning a situation where you have your oxide, perovskite, chromia, barium titanate exposed, but there's a shell of metal around the outside of the atom probe needle. So in that case, do you expect us to have yield effects, or do you expect us to, have our photoionization mechanism still working well?
Well, I think if we put on a conductive coat, we more or less put on a heating pad around our tip. So we induce heat in the coat that heats our sample that then facilitates the evaporation. So I would rather not expect the ionization in that case.
That's really interesting. And something that's relatively easy to try, I would say, because in situ
Yeah.
coating has become quite popular as a quick and easier way to coat sharp tips. So thank you. Okay, next question. Can we analyze titanium nitride HZO and silicon interfaces? So I don't know if HZO is referring to hafnium zirconate. So if someone would like to clarify that. But, materials wise with this stack, I don't see an issue for atom probe. If the question asker is indeed referring to hafnium, titanium nitride is a typical gate material in semiconductors. Hafnium oxide is a high K material. So these are fairly okay, so hafnium zirconium oxide. Yeah. I don't see an issue here. High K is often used in semiconductors. Obviously, silicon is a channel material and a substrate material. So this is, a relatively routine materials combination that we see in semiconductor. And one of the things that we've seen is that, once again, deep UV is improving yields in semiconductors. Now, we could analyze this in the LEAP 5000 pretty effectively as well. So yeah, I would say it's a pretty good application for atom probe. Okay, next question. Thanks for the answer, Katie. Same also to Severin. Did you see any strange behavior in the mass spectrum due to the laser interaction with the material? So influence of hydrogen on, I believe that this question is referring to chromia. So any influence of the laser interaction with chromia and influence on hydrogen?
Yeah, so the hydrogen peak was more or less as expected. We see some funny peak shapes that we discuss in a previous paper just on the evaporation of chromia, where we think that this is because of dissociations. In general, we see maybe different kinds of molecular ions than we would have expected. And this is, I think, because we have lower field and lower temperature due to this mechanism.
Yeah, I think we have to expect that the field is different, because we're pulsing with the combined pulse here. So yeah, that is a very good question. Okay, next question, and let's both answer this, Severin. You first. In voltage plus laser mode, could it be more or less likely that the sample would be fractured? So what's your opinion, Dr. Jakob?
So what we've seen is that the yield is similar to laser mode. So really great improvement in the yield for tricky samples.
Yeah, and I think I would definitely agree with your answer. We've seen that the yield is very close to laser mode. I think a lot of folks are pretty afraid to use voltage mode on a fragile sample, maybe an oxide, but I have no issue running simultaneous pulsing on these, and I would say that the yield is very similar to what we expect in laser mode. Okay, another question. Yeah, very good question. The oxygen measured was only 35% in BaTiO3. It should be 60%. Did you try lower laser pulse energies? And this is a very perceptive question. We do see a deficiency of oxygen in MLCC materials, and this is related compositionally to the laser energy that we choose. So we've done a little work using scripted acquisition to step through different laser energies to look at the composition. And indeed, we do see a higher amount of oxygen with lower laser pulse energies. However, there is likely a strong influence on composition with oxygen neutral formation, so we still do experience a deficiency. If you are doing doping studies or compositional studies with barium titanate, you may want to work on a ratio or metals basis for this because of that oxygen deficiency to, have an accurate picture of the composition. Okay, so we'll just give a couple final minutes for any last questions. And while we wait for that, just another question for you, Dr. Jakob. Just wondering a little bit about if you see differences in field evaporation with deep UV depending on how the material is grown. So I think you had looked at a couple different ways to grow material. Do you think, the growth of that has any influence on field evaporation?
Well, in our study, we tried uh, our procedure on thermally grown chromia as well as chemically vapor deposition. And the CVD process we used to have a very clean chromia because the thermally grown has about 2 to 3% of titanium, so a lot of impurities that might be called doping in that case. But actually, we see no different evaporation in terms of the mechanism. There might be something about the efficiency, or so we have some little heating that facilitates the whole generation. And there might be some difference because we might have some different absorption and different recombination of holes with some surplus electrons, that kind of thing. So I would be really excited to see a study with different doping contents in the material and also maybe have positive doped and negative doped and the
Yeah, I think that
comparison
would
of
be
that.
very interesting. A little bit challenging to make that sample, I think, at least in a uniform way.
Well, it could be like several tips, I guess.
Yeah, no, that's an excellent idea. Now, I'm curious, since we had a question about the oxygen deficiency, did you also observe this in chromia?
Yes, we did. And we actually, when we went to really, really low laser pulse energies, like 0 point something, then we approached
Correct composition.
the almost stoichiometric concentration.
Okay, I think that's all the questions we have. So I'd like to thank you again, Dr. Jakob, for being here today. It was wonderful to have you. Our next webinar is scheduled for February 17th on a really exciting topic of fusion materials. So hope you can join us, and we'll see you next time.
Thanks
Bye-bye.
for having me.